So here's another quick video using a PIC16F1619 to do some accurate frequency calculations. It was originally shown on the Microchip forum. There was a request asking how can they use PWM to create very accurate frequencies, and I thought, well, what's this for? And it turns out it's for generating a tuning device for musical instruments. So I thought, okay, well, let's look at a different way. And what this method does is that it uses a phase accumulator in software, and every there's a rate of 31.25 kilohertz. It updates a phase accumulator in software and outputs an updated value to the DAC output. So if I show you the interrupt routine here, you can see the ISR there, and you'll see that it actually sets a next DAC value and then prepares the next value here. And it also, because it's going at 31.25 kilohertz, I also set a little flag every second, which is used later on, which are in the super loop. And other thing I've done is when I initialize it, I set it up with the phase incrementer to give you 1000 hertz for a couple of seconds, so that we can just make sure it's all working. I've got a sine lookup table here that I generated in Excel, and a fair bit of initialization goes on here, and you'll see in here within the super loop, what it does is every 3 or 4 seconds, what it does is it updates the phasing. So I actually change frequency every 3 or 4 seconds, so we can have a listen to it. And I've prepared here, these are the actual frequencies of chromatic scale. So let's give it a go. I think I'll reset it, and let's go. This is my 1 kilohertz, and you can see the trigger frequency there. This is a 440 hertz concert A, and I'm going up in a chromatic scale now. I pinched these figures off of the interweb, so hopefully these are all right. Now I leave it for 4 seconds just to give us a reasonable trigger frequency readout. Okay, and it just restarts again. So another question that we had was, how good is it if up in higher frequencies? So if I basically shove this up, multiply the frequency by 4. Oops, I've done this in the wrong place. Times 4. Oh, by the way, you might ask why it is that I've got this rather than a normal PIC. This is a debug header, and I'm using this because I'm using the debugger with it, the hardware debugger, and the hardware debugger uses the DAC out pin. So if you use a debugger on a normal chip, the DAC out pin is pinched by that. So I use the debug header, so it means I still have the DAC out, but I can still debug. So if I run this again, this time at a higher frequency, it'll still do the 1 kilohertz right at the beginning, which we'll see in a moment once it's loaded the software in. So there's your 1 kilohertz. This is as you can see, you get some interesting artifacts. This is just aliasing because we're sampling at 31.25 kilohertz, and so my phase accumulator is slowly changing phase, so you get this sort of beating effect. Okay, so what I'll do now is I'm just going to slightly change this code so that instead of it going, we do it a little bit quicker so that we get it every single, it increments every single time. Hopefully I've got this right, but if I haven't, I do apologise. So hopefully every second it'll increment. If I get it wrong, I do apologise. Okay, and I guess we should just do the sort of standard concert 440 rather than up a few octaves above. Let's have a look. I think that was let's see, it was 2 octaves high. So this is your standard. Going to start off with the 1000 hertz, the 1 kilohertz for a second, and then it'll start. Then it'll go concert A. Every second it'll go up on the chromatic scale. Okay, well, hopefully that's useful, and hopefully that helps somebody. Cheers.